Thank you. So it's a pleasure for me to be here talking about the Spark notebook, how it works. It integrates with sparkling water. And we work with genomic data. The topic here is that we show mostly a process of analyzing data. We're not here to do advanced genomics. It's more a toy case, but showing the flow of going from data analytics to production, maybe, of services from this. So the line of the talk is that we'll make a brief introduction on Spark, how the Spark notebook brings interactivity to Spark. Now, how do you deal with domain-specific thingies like genomics on Spark with specific libraries? What the data is, what do we want to do with it, and how we work with H2O to resolve the problem we want, and then make a show of how we do that in the Spark notebook in practice. So, as Vinod mentioned, I work with Andy Petrella in Dataframe, a startup we founded a couple of months ago. We have a background mostly in mathematics, physics, and we worked in topics like geospatial, bioinformatics, finance. And then we moved towards distributed computing technologies because they're so fascinating in the current data world. We're Spark trainers and focusing on these technologies right now, doing some data analytics. So first, who is familiar or is using Spark regularly? So a few. So Spark is a distributed computing framework, a general purpose, large-scale data processing engine. So it's very generic, and it provides very interesting interfaces. For example, the Spark SQL is providing really interesting optimization for the execution of the process you want to define, if you can define it with the SQL algebra, I mean. There's a streaming in the form of micro-batching, so it's not event-by-event processing, but batching by time windows that can be quite short if you want. There's a library for large graph processing and a library for machine learning as well. Now, the interesting thing about Spark, if you compare with other technologies that were in the place maybe before, like Hadoop MapReduce, is that it's really focusing on certain important things with respect to performance. So it's leveraging as much as possible memory usage, because obviously it's a fast data access. It also optimizes computation execution. And this is thanks to the fact that it's lazy evaluation. When you write code in Spark, you're actually defining transformation, and the execution of this transformation in the cluster only occurs when it's required. That means that Spark is actually building, is able to optimize, in some way, compile the best way to execute the task you want to do. And so for complex tasks, it's really more performant. And the programming model is easy, so it's using the easy features, I would say, of functional programming. So it's very similar to what you would do in Python or in R if you're using the Scala API. OK, now other things it brings. Because it's written in Scala at the start, you have access to a REPL. That means that you can work interactively with Spark. So you can talk to your cluster and ask him to do tasks for you in an interactive way. So you have a direct feedback on the operation you're defining, which is really interesting from a development perspective, either from an algorithmic point of view or really to explore what's in your data. And interestingly, it's interactive and it's working at any scale. That means that you can work with your entire data set on your cluster this way, or if you want to just develop some functions, you can do that locally on your laptop without having to install many things like you would do with Hadoop. And the Spark notebook is actually bringing a user interface that is convenient for the user. Most of you, I guess, have used interfaces like notebooks. It might be IPython, it might be R, whatever. The specifics of the Spark notebook is that it integrates directly Spark, which means that you install the Spark notebook, you run it, you don't have to install Spark to get it running because it ships the dependencies directly. So you start the process, you have a web interface where you can start notebooks, creating everything needed to get Spark running, and you can, as we see later, connect these notebooks to different clusters if you want. We focus on Scala because it provides us some interesting features like types, and types are helping us all the time. We know at every step what we are doing, what kind of object we are manipulating, so we're kind of really strongly biased towards those languages. Another reason is related to the fact that we analyze data, and in the exploration phase, what we want to know is there value in the data? But in the end, you want to exploit that value. So you want to transform, knowledge that there is something interesting in the data into a service. And to do that, we want to streamline the process, and we need to be able to transfer what the data scientist has done in the form of scripts, probably, into something that the data engineer is able to give to the DevOps for deployment as a service. And working in the Scala environment is really making the game much easier, and that's why we think it's interesting to focus on that language. Also, yeah, Scala for data scientists, what are you talking about? There is no good way of charting and things. So we're working quite hard on having reactive charts, an API that is entirely written in Scala. So no need to develop in JavaScript to get some plots. As I said, it's easy to install. There is no dependencies, and you can connect to multiple Spark contexts. That means that with your single notebook environment, you can develop working on local, then having another notebook connecting to a cluster, another one connecting to another cluster, and this with the same environment, which is very convenient because obviously you don't always develop process on the same infrastructure. So that's for the Spark notebook. Because we only have half an hour, the only demo of the Spark notebook will come in a bit later. So I go directly I continue with the talking, and we'll get to the demo afterwards. So let's go further with the case we want to deal with, that is genomics data. If you want to process data that is generated from the genomics world, you need to have domain-specific libraries to do that, because the raw data comes in very specific format and are stored in special storage systems. And so you need an interface to get from the data to your distributed computing environment, Spark in our case either. And the guys at AmpLab developed the Adam project, which is a very interesting one because it brings on the table, I think, what is the right way to deal with big data nowadays, especially transforming something that was legacy technologies, I would say, to what we see nowadays in IT. The most important thing they defined is actually a schema, because they want to structure the data in such a way that it's possible to store it in a compact format that is distributed over the network. What I would call kind of legacy or a standard format try, of course, and are successful in compressing the data, but they are not well designed to distribute data and partition it correctly on a cluster. To do that, schema is key, and so the technology they use is Avro to define the schema and Parquet to store the data in a distributed fashion, and of course they provide APIs, so definition of objects and interesting methods to manipulate this genomic data. The data we deal with comes from a project that is the 1000 Genomes project. It's a project that started from I think the late 5 or 6 years ago and lasted 4 years collecting data, so mostly sequencing about 1,000 individuals taken from different populations in the world to gather knowledge about the genetic variation that are present in the human population. So the data we have is those genomes, and we'll focus on variation in those genomes here, and we know from which region of the world this individual come. So this is the data. It's called genotypes. That is, what is the variation on a chromosome between different persons. So chromosome, is a long chain that we can represent as a string. And this string is built from letters, from a four letters alphabet. And some positions can change from one individual to the next because of a mutation occurring naturally. And this mutation can spread in the population from one generation to the next. And all those differences make up what we are in terms of, ingredients of the biochemical soup that we are kind of made. And so this is the data we focus on. The amount of data, as I said, it's about 1,000 samples. It's very few, but it's quite a large number of features because in such a population you have of the order of 30 to 100 million variation. So that's the number of features. So we can foresee that we'll hit some problems here. Okay, what can we do with this data? The thing we do here is to make population stratification. In marketing, you would call it customer segregation. The important thing is that we want to maybe downstream make some analytics, make some drug response analytics to predict drug response and things like that. If your population is heterogeneous, you may have problems modeling and having good prediction. So stratification is usually a first step when you are dealing with such population data. And okay, why not do that with deep learning and H2O in particular? And do that from the Spark notebook, because we'll connect to the data through Spark and with sparkling water. So H2O, we all know why we want to use that. So it's a very efficient MapReduce implementation with a really optimized structure for the JVM and a very good algorithm for machine learning. Now, I guess you have heard about sparkling earlier in this conference. In 2 words, if you have a Spark and you want to work with H2 at the same time, you need just a few things. Here, Spark will be the driver of all your computation because it's Spark that connects to the data. It's using the Spark notebook that allows you to define a complete flow that you will be able to ship later into production. So you want everything to be done from Spark, and H2O being used as a tool to leverage some specifics of the machine learning. So to do that, you need your Spark context, which is the way you interact with your cluster in Spark, to be able to create for you an H2O cluster, because you don't want to deal with 2 deployment of clusters, okay? And so that's what sparkling is providing. So functions that allow the Spark context to build, actually to create those H2O nodes in the Spark nodes. So each Spark executor will have its own instantiation of the Spark of a H2O node, and so you have a cluster living within Spark. And then, because the data is mostly kept in memory in Spark, you need a way to transfer the data, which is distributed in partitions, into the H2O nodes. So there are functions to transfer, to make actually a copy of the data that is in Spark, in memory usually, in memory then again, but in H2O as a frame. And then you ask from a client, which is the third ingredient you need, an H2O client in your Spark application to make computations and get the data back into Spark as needed. You can check out the product for sparkling water. Okay, now let's dive into the thing. and run and look at the notebook that is doing that. So as I said, the Spark notebook, it's just an application. You download the tarball. Maybe I can just show you the page where you can do that, sparknotebook.io. So from there, actually, you simply choose the different version you want, the version of the notebook, the version of Spark, Scala, and the most important, the Hadoop version. And you can download it as a tarball or a zip or a Docker. You uncompress the thing, and you just launch the application. There are a number of distribution available that are already compiled by other users. So you simply download the thing, you run it, and if you do that on your laptop, you will get access to this page, which is a browser giving you access to different files that are actually notebooks. And this notebook, for example, so I click on the link, and I get this notebook started. And this notebook is starting a complete Spark application for you. So there is what is called a Spark context that is created, and this Spark context is a gateway to the cluster. If you work in local, it will just use the local resources you have on your computer. If you're working on a cluster, you may ask it to connect to the cluster. Let us look at some metadata here. So we can define actually here what is the Spark configuration. So for example, in this setup here, it automatically connects to the Spark master. We're working on an EC2 30-node cluster here. And because of the environment variable, it's automatically connected to the cluster. But if I only do that in local, it would run in local as needed. Now, other interesting thing is that I want to work with H2O. So I need, of course, the sparkling dependency to be shipped in my application. So I just defined here some custom dependencies. So the only specifics for having sparkling working is this line. Okay, and because I will be doing deep learning and the algorithms are not shipped, are not a dependency of sparkling, I just need another one to get the H2O algorithms available. So it's very easy to get that working. And then I have other domain-specific libraries that I use for genomics. So it's fairly easy. And then you get this interface where you simply define blocks that are either a markup for annotation or code to be executed. I will go through this notebook pretty quickly. Just the idea is to show you how this works. So you import dependencies to get everything running. Then I point here with a variable to the location of the files. So my genomic data is located on S3, and I use the Adam specific call from the Spark context to load the data. So this actually creates what is called an RDD, so a resilient distributed data set. So it's a data set, it's an object on which I can define transformation in the Spark API. So it's a kind of distributed collection split over my cluster of object of type genotype. And this type genotype comes from the Adam library. It's a pretty complex object with many dependencies. So I want to transform this before going into H2O, of course. And we do that later. For example, defining filters. So I have my collection here. I apply a filter. And in the filter, it takes a function here that says I want only the variants that are between this position and this position on the chromosome. So you see it's Scala, but it's very simple Scala. You don't have to get deep into this crazy type level programming. It remains very affordable, I would say, for a Python developer. So I make some filters. I have a couple of populations I want to work with. So another interesting feature here is that I'm working with data that is not complete. So I have individuals, I have their genotypes and the positions of these variations. That's interesting, but I want to make prediction or make a model of the different populations maybe. So I want to join a list of populations with the list I already have here. So to do that, of course, you need the right interface, and Spark is providing that. And here, what I do is that I actually grab the file that is located on the on FTP server that is published, and I grab it directly from the Spark notebook using a system call. So I don't have to go to a shell doing this operation. I want my notebook to be consistent and do the complete work. And it's pretty easy. You just write the command, which can interpolate variable into the string, and with the lingo of the double mark here, you get a system call here. And we see that the data is just the sample IDs and the population they belong to. And after we do population stratification, we'll be able to compare if the unsupervised learning finds back those populations or not. Okay. And then what I do is that I ship this list of populations into the different nodes in the cluster. It's also a Spark-specific operation to optimize the way you can join the data. So I make my selection. I define some helper functions because, as I said, the genotype object is too complex to deal with. So I want to flatten it in a simple structure, and these functions actually allows that. Then I do some, if the data is complete, and I make other filters on the data because, as I said, there are many, many features, so I will only select the ones after computing the frequency of the mutation I'm looking at. I will only select the ones that carry the most information. So I do that in another filter here. And then when I've done that, I have actually a list of objects that contain just the information I want, and that it's a complete data set, so there is no missing data, and I'm ready to go towards machine learning. To do that, I have a last transformation to make. I need to go to the Dataframe API of Spark because it's much easier to transform data from a data frame from a Spark data frame to H2O than from this RDD of genotypes that I had before. And so to do that, you need the SQL interface of Spark that is loaded here. So this creates a data frame. So now I have really the same kind of object that you would have in R or a frame in H2O. So it's really now a matrix. And this matrix is typed, so you have columns with a type. So it will be easy, if I may say, for the H2O, the sparkling to transform the columns from this data frame in columns of the right format in H2O. Now H2O, how does it work? We take this function. So we instantiate this H2O context object with the Spark context as parameter, and we just start it. We could set the number of executors we want. So here I have 30 nodes. I may want maybe only 5 to make the processing. We'll see that it would have been clever in that case because we don't have that much data. And so when you do that, you have now access to an H2O cluster, and it's actually available. So here I'm on the driver, and I ask on the port, on the usual port of the flow of H2O, and I have actually access to it, and I can make calls to H2O. So I have the two interfaces. So if I want to check what happens from when I do some Spark execution, I can go into the Flow API to see what happens. Okay. Converting a data frame into an H2O frame, really easy. You take the H2O context and you apply the function as H2O frame. The argument is the data frame, and you get an H2O frame that you can actually see here as this frame RDD. So it comes from an RDD, and it has been transformed into a frame. And then you can apply, splitting the frame between a validation set, a training set, and a test set. And these operations you see here are just pure H2O client operations. So there is no Spark involved here anymore. We're only doing processing in the H2O world. We do some deep learning, exactly the same. It's the Java API that is running here. We train the model. And then, of course, when you go into Flow, you have nice things because you can actually look at the models, look at the scores here, and view these interesting statistics. If I want to get those statistics, I need to write a function that is here that computes a confusion matrix. So the idea is that here I compute a score from data given the model, and then I get this data back into a data frame. So H2O context as data frame. So I bring back the data into Spark, and then I can process the data, making my computations, my countings to get this confusion matrix available. Okay, so you see it's pretty easy to get that working here. So I'm gonna wrap up now. Okay, so you've seen that the integration in an interactive Spark notebook works pretty well, and it's pretty easy to get that working. As I mentioned, the idea is to get an easier way to streamline, the process of having the data scientists develop a processing pipeline models, then having this going into production. So being able to transform the data scientist work into a service that is queryable. There are many jobs that are involved into this process, and using this kind of environment as for aim to streamline and making easier to get communication between the different jobs and having the time to market your model much shorter. So in summary, Spark and the notebook are interactive. They leverage the distributed infrastructure. If you work with Genomics, there are storage formats that are optimized to work with the data. Spark works well with H2O. It's able, in a nice way, to initiate computations. And the project share that we develop at Dataframe aims at streamlining this collaboration you need to get your data application into the market faster. So I would like just to thank the people that we interacted with to make that work. The guys at AmpLab, Frank and Matt, Neil Ferguson of University Imperial College London, who made a work on integrating Adam into Sparkling, and Vinod and Michael for the discussions we had here.
We have time for one question.
Hi, I came a little late, but I just want to ask, so you were working with RDDs and data frame. Why would you just not work with data frames directly?
The question is?
You were going back and forth, right?
Yes.
From RDD,
yep.
Data frame, then H2 or data frame. And
the reason is that I use Spark as my application development environment. So everything that goes in or goes out is from this application. So I cannot get the data into H2O and leave it there. It has to come back at some point. See? Of course, I could ask H2O to read the data as well. That is completely possible. There is no constraint on that. Spark supports its own data frame definition. So there are two different things. There is the Spark data frame, which is a representation of data and on which you can make some kind of SQL queries. But there is the H2O frame, which is a completely different object. But we copy the data from one format to the next because Spark is able to process directly data frames. H2O is able to process directly H2O frames. So it's a copy of the data and changing the internal representation of the data.
Thank you, everyone. Thank you, Xavier, for the wonderful talk.
Yeah, I'm glad to talk to any of you.
Yes. Unfortunately, we're out of time, but Xavier will be available here this afternoon. So if you guys want to have any questions about Spark Notebook or the implementation, feel free to grab him. Thank you.